Sometimes we're interested in using properties of logs to combine an expression that has more than one logarithmic term. So if the instruction says to write as a single logarithm, we should be thinking about the direction of these properties that brings multiple logarithmic terms into a single log. This first one, we see all the bases match, so it is okay to use the sum of logs as the log of a product property, and there's no reason that we have to restrict this property to just 2 terms at a time. We can take 3 terms. We have a sum of 3 terms here. We can still write this as the log to base 8 of a product of all 3 of these inputs. So 6 times 2 times 5 gives us the log to base 8 of 60. The way we handle this at this stage is, if that were a value that we know, for example, if 60 were a power of 8, or if this had said the log to base 8 of 64, then we would go ahead and evaluate it. But this is an irrational number. This is something we could put into a calculator. Well, maybe we don't know how yet. But a decimal approximation is not generally considered to be simplified. So if there's no way that we can write it in an exact simpler form, we just stop exactly as it is. Looking at this second example, it's a little bit more complicated. We have 3 terms again, but one of the things that makes it more complicated is that one is a subtraction and the other is addition. So we have 2 different properties at play, and we have to be a little bit careful about what we do with things. The other complicating factor is this scalar multiple of 2 here. This isn't exactly a sum of logs if it's a log term plus 2 times another log term. So we have to think about both of those things as we decide on an approach. What I'm going to choose to do is resolve the 2 first. It's not going to be 2 times a log if I use property 4 and move it up into the exponent. So I'll rewrite this whole expression as the natural log of x minus the natural log of 2x plus the natural log of y squared. Now I have an expression that is just sums and differences of logarithms. I can apply both properties 2 and 3 at the same time if I just think of this as a string of added and subtracted logs and keep track of which ones are positive. If the whole logarithmic term was added, then its argument, in this case x, goes into the numerator. I'm just going to write top because it's a little bit shorter. If the whole logarithmic term was subtracted, then its argument goes into the denominator of the input to the log, or the bottom. So again, here we have an added log term. Its argument is going into the numerator, or the top. So what I do is I just write it all as a single log in one step. It's easier than doing this 2 at a time because you can end up with a triple-decker fraction or something if you try to do it just 2 at a time. Sorting everything out in one step is actually easier. So the 2 that I identified as going into the numerator in red are x and y squared, and these are now multiplied because remember, a sum of logs is the log of a product. The 1 that I identified as going into the denominator is that 2x. So that I have a single log of an expression consisting of all multiplied or divided factors. And the only other thing I have to do at this stage is reduce. I can see I have a factor of x in the numerator. I have a factor of x in the denominator. Those are going to cancel each other out, but nothing else simplifies in this particular case. So I'll go ahead and write this as the natural log of y squared over 2. The most common mistakes on something like this are either to accidentally have that y squared end up in the denominator, because sometimes we get affected by that minus that showed up earlier in the expression. Or sometimes I will see another thing that I want to really discourage. When someone is sorting everything out, I'll often see this. Ln of x goes in the top times ln of y squared goes in the top over ln of 2x goes in the bottom. And then sometimes I even see a student get from this to the correct next step. But I really want to emphasize that this in-between step is absolutely incorrect. All in one step, we go from a sum of logs to a single log, right? Just one log that is a product. There is no in-between step where we have a product of logs, right? So try to avoid doing this because it's incorrect, and it may lead you to do incorrect things in other contexts. Just skip that and go straight from a sum and difference of logs to the log of a product slash quotient. In contrast to the instruction that says to write as a single log, we might get something that starts out as a single log and we are asked to expand. This means go the other direction, take it into as many log terms as you can in a reasonable way, right? So we're going to write this as a sum of logs. And we're generally just going to apply all of the properties that we were applying in order to get things closer together. We're going to apply all of those properties in the other direction to expand it out. So in order to do this, what you need to look for at each step is the outermost operation, by which I mean at least within the log, right? The log is the outermost operation. But inside the argument to the log, there are a lot of things going on. There's adding, there's squaring, there's taking a square root, there's multiplying, but there's an outermost operation, which in this case is division, which is if we were evaluating this expression, it's the last thing we would do. So the outermost operation is division here, and that's the first one that we are going to look at for expanding this. The log of a quotient is the difference of logs. So I'll write this as log of x plus 1 squared minus the log of everything in the denominator. Square root of y times z squared plus 1. And then I keep applying this kind of reasoning. Looking at each log term now, log of x plus 1 squared, there is addition and there is an exponent, but the outermost operation, because of the parentheses here, is squaring. So that's the one I'm going to look at for whether or not a property of logs might apply. And yes, a property of logs does apply. I can bring that square out as a scalar multiple. Looking at the second logarithmic term, the outermost operation here is is multiplication. The product of the square root of y and the whole factor z squared plus 1 is my outermost operation, so I can use the property of logs that says the log of a product is the sum of logs. So in the next step, I have 2 times the log of x plus 1 minus, I'm going to use square brackets here because I'm going to rewrite this log as a sum of 2 logs, but I want to make sure that that whole sum gets subtracted. So this is the log of the square root of y plus the log of z squared plus 1. Now for each term, I will again look and see what the outermost operation is. Here, the outermost operation is the only real operation left, is addition. We have a sum. So what I want to do is think about, is there a property that handles the log of a sum? And sometimes we get a little mixed up with the property that handles a sum of logs, right? But there isn't a property for a log of a sum. In fact, the log of a sum of two terms, we have to leave it alone, right? So we are done with this one. This next log term, we have a square root. The only reason we can do something with a square root is that the square root is the same thing as a power, right? The square root of y is the same thing as y to the power 1/2. So really the outermost operation in this particular expression is a power, and a power we actually do have a property for. We can bring that power out to the front. Looking at this last term, we have a power and a sum, but the outermost operation is a sum. So I can't do anything with that power. Once I get to the log of a sum, I have to stop. So I can't bring that power 2 out because it doesn't apply to the whole expression. So this one I'm stuck with. I have to accept it as it is. I'll go ahead and while I'm rewriting this with the power 1/2 brought down, I'm also going to distribute in this sign here to both terms just so that I don't have to rewrite this expression another whole time. So this is going to be 2 times the log of x plus 1 minus 1/2 times the log of y minus the log of z squared plus 1. So we know we're done when the outermost operation in each log does not have a property that would allow us to rewrite it. We don't look further at other operations in that expression.